For many aqueous solution reactions, we can reduce the complete chemical reaction down to what we call a net ionic equation, because not all of the ions in solution are going to participate in a chemical reaction. And so what a net ionic equation tells me is the species that are involved in the chemical change that is taking place. We're going to go through the steps to taking a complete molecular chemical reaction or chemical equation and reducing that down step by step to a net ionic equation to see exactly what is happening in that reaction. First, we are going to write the balanced molecular equation. Let's say we're looking at the example of lead nitrate. This is an aqueous solution. And reacting it with potassium iodide, another salt in aqueous solution. If this reaction is going to take place, we would have to have a driving force, and we will look for that driving force after we predict what the products would be. So we would take this as if it were a double displacement. We have two salts here, so by swapping the two metals, we would get lead iodide and potassium nitrate. And we can look at our solubility chart to determine whether or not these will be soluble or insoluble in that solution. It turns out that lead iodide is a solid, and so that would precipitate out, and potassium nitrate would remain soluble. So this, as written, is our complete molecular equation. We need to balance it, okay? So lead appears once on each side, nitrate appears twice here, but only once here, so let's put a 2 here. Then potassium appears once here, but now twice here, so if we put a 2 here, and then iodine is now twice on the reactants, twice in the product. So everything is complete. At this point, we're ready to do the second step, which is to dissociate soluble, strong electrolytes into their ions. Since lead nitrate is a soluble, strong electrolyte, we would separate into lead 2+ cations plus 2 NO3- anions. And I'll keep the phase notation there. For potassium iodide, this is a strong electrolyte. It's our ionic compound, and so it would be separated into 2 potassium ions and 2 iodide anions. So that's for the reactant side. And then the product side, the lead iodide is a strong electrolyte, but it is not soluble. So it's going to stay as one unit, as a solid. And then we have the potassium nitrate, which is a soluble, strong electrolyte, and the nitrate anion we squeezed in there. Okay. The next step, now that we have our complete ionic equation, is what this would be called, is to eliminate what we call spectator ions. And a spectator ion are those that appear on both sides of the chemical equation. And much like in a mathematical equation, we can remove things that appear on both sides. So what do we see? We see that NO3- appears also on the product side, so there are 2 of them. We can cancel this out. So that's going to go away, and that's going to go away. Potassium appears on both sides, so that's going to go away, and that's going to go away. This reduces down then to give my net ionic equation. So I have lead 2+ cations reacting with I- anions to give lead iodide as a solid precipitate. And this tells me if I ever want to make lead iodide, all I need is lead cations and iodide anions. So rather than using lead nitrate and potassium iodide, I could use different reagents. I could use lead acetate, for example, and HI, another strong soluble electrolyte, a source of I-. Okay? So there are a number of ways that you could put this together in order to achieve this outcome. But the very simplest thing that's going on here is what is denoted by the net ionic equation. Thanks for watching.